Mecanum wheels enable true holonomic motion, meaning the robot can instantaneously translate and rotate independently, unlike standard differential or Ackermann drives. This capability stems entirely from the passive rollers angled at 45 degrees relative to the wheel's rotation axis. When the wheel spins, these rollers allow slip perpendicular to the wheel plane, generating a force vector that is not purely tangential. The key is that the force generated by the motor torque is always directed along the roller's axis of rotation, which is offset by 45 degrees from the chassis centerline. This geometric constraint dictates the entire kinematic model. Understanding this fundamental force direction is the prerequisite for calculating any omnidirectional movement. Each Mecanum wheel is essentially a set of barrel-shaped rollers mounted around the circumference. For standard configurations, the roller axis is fixed at exactly 45 degrees relative to the main wheel axis. When the wheel is driven, the motor torque applies a force, Ft, tangent to the wheel radius. However, due to the roller geometry, the resulting ground reaction force, Fg, is constrained to act along the roller's direction. We decompose this Fg into two components, Fa acting axially along the chassis, and Fs acting sideways, perpendicular to the chassis. Both Fa and Fs are proportional to the motor torque and the cosine or sine of the 45-degree angle, meaning Fa equals Fs in magnitude for a single wheel.
Consider a single wheel rotating at angular velocity omega. The resulting velocity vector Vw has components Vx and Vy in the chassis frame. Since the roller angle is 45 degrees, the velocity vector Vw is defined by the wheel radius r and omega. Specifically, Vx equals r times omega times cosine 45 degrees, and Vy equals r times omega times sine 45 degrees. The direction of the resulting force vector depends on the roller orientation, which alternates between positive 45 degrees and negative 45 degrees across the four wheels. This alternating pattern is crucial for ensuring that opposing side forces cancel out during pure forward motion or sum up during pure strafing motion. Mecanum systems typically use four wheels arranged in an X pattern. This means the front left and rear right wheels have rollers angled identically, say positive 45 degrees, while the front right and rear left wheels have rollers angled at negative 45 degrees. This symmetry ensures that for any desired motion vector Vc, the forces generated by the four wheels can be resolved into a net force Fc and a net torque τc. If the wheels were arranged in a parallel pattern, pure strafing motion would be impossible because the sideways forces would cancel out, leaving only rotation or axial movement. The X pattern guarantees that the side forces either constructively interfere for strafing or destructively interfere for axial movement. To achieve pure forward translation, Vx, all four wheels must spin at the same angular velocity, omega. Since the roller angles are symmetric, the sideways force components, Fy, generated by the front left and rear right wheels are exactly cancelled by the Fy components generated by the front right and rear left wheels. The axial force components, Fx, however, all sum constructively. The resulting chassis velocity Vx is simply r times omega. This demonstrates the simplest case where the complex roller geometry simplifies to standard differential drive kinematics along the primary axis, provided the side forces perfectly nullify each other.
Achieving pure sideways translation, Vy, requires the wheels on one diagonal pair to spin in the opposite direction of the wheels on the other diagonal pair, but all at the same magnitude of angular velocity, omega. For example, front left and rear right spin clockwise, while front right and rear left spin counterclockwise. In this configuration, the axial force components, Fx, cancel out completely. Crucially, the sideways force components, Fy, now all point in the same direction and sum constructively. The resulting chassis velocity Vy is r times omega. This is the defining kinematic mode of the Mecanum system, utilizing the 45-degree roller angle to convert rotational input into purely lateral movement. Pure rotation, or spinning about the chassis center point, requires all four wheels to spin in the same direction, but the wheels on the front axle must spin opposite to the wheels on the rear axle. Alternatively, all four wheels can spin in the same direction, but the magnitude of the angular velocity must be proportional to the distance from the center of rotation. For a standard spin, if all wheels spin at the same magnitude omega, the resulting axial and lateral forces cancel out, leaving only a net torque tau. The angular velocity of the chassis, omega, is proportional to r times omega divided by the quantity L plus W, where L and W define the chassis dimensions. The general kinematic model relates the desired chassis velocity vector vc, defined by vx, vy, and omega, to the required angular velocities of the four wheels, omega I. This relationship is linear and defined by a 3x4 Jacobian matrix, J. The equation is vc equals j times omega w, where omega w is the vector of the four wheel speeds. The matrix elements incorporate the wheel radius r, the chassis dimensions L and W, and the sign convention for the 45-degree roller angles. This matrix is the foundation for the inverse kinematics calculation, which is necessary for real-time control.
Inverse kinematics is the process of determining the required wheel speeds, omega I, given a desired chassis velocity, vc. This involves multiplying the desired velocity vector by the pseudo-inverse of the Jacobian matrix, J dagger. The resulting four equations define the required omega for each wheel based on the target Vx, Vy, and omega. For example, omega 1 equals 1 over r times the quantity Vx minus Vy minus the quantity L plus W times omega. Accurate execution requires precise motor control, typically using closed-loop proportional integral derivative controllers to maintain the calculated speeds despite varying load and friction conditions. The ideal kinematic model assumes perfect rolling contact, but real-world performance is limited by the friction cone. If the required lateral force exceeds the maximum static friction available between the roller and the ground, slip occurs. Slip drastically alters the actual velocity vector, leading to control instability and inaccurate positioning. High acceleration or rapid changes in direction are particularly prone to inducing slip. Minimizing slip requires careful tuning of acceleration limits and utilizing high-resolution encoders combined with inertial measurement units for feedback correction, ensuring the commanded velocity matches the actual achieved velocity.